Michelson's interferometer, wavelength of monochromatic source of light. So this experiment is to determine the wavelength of monochromatic source of light using Michelson's interferometer. Materials and equipment required. Michelson's interferometer setup. Monochromatic source of light, sodium vapor lamp. The Michelson's interferometer is a device that produces interference between two coherent beams of light. Light from a monochromatic source is split into two beams of equal intensity. One part of the light travels a different path length than the other. After traversing different path lengths, the two light beams are brought together to interface with each other. The interference pattern can be seen on a screen. So the Michelson interferometer consists of two highly polished front quarter mirrors M1 and M2 placed mutually perpendicular to each other. The mirror M1 can be moved with the help of a micrometer screw, and the distance moved can be noted on the micrometer scale. The mirror M2 with the screw on its back can be tilted slightly. A beam splitter B, which is semi-silvered on its rear side, is placed between the mirrors M1 and M2 at an angle of 45 degrees to both the mirrors. A compensatory plain glass plate C is placed parallel to the beam splitter between the beam splitter B and the mirror M2 to make optical path lengths of both the beams to be the same. Light from monochromatic source falling on the beam splitter is divided into two beams of equal intensity. In this way, division of amplitude takes place. The transmitted beam traveling towards mirror M2 and the reflected beam traveling towards mirror M1 are reflected back by the respective mirrors and made to interfere to produce interference pattern on the screen which depends on the path difference between the two beams and the angle between the mirrors M1 and M2. So now we will move on to the procedure for determining the wavelength of a monochromatic source of light. The first point is the adjustment of the interferometer to obtain circular fringes. So the position of mirror M1 is adjusted such that the crosswire coincides with any one of the dark fringe or central dark fringe. The micrometer screw reading is noted. Main scale reading is in centimeters. Note down the reading of the coarse adjustment knob vernier 1. Multiply this reading with the least count 0.0. So in order to determine the wavelength of the monochromatic source of light, the interferometer is adjusted to obtain circular fringes as shown. Then the position of mirror M1 is adjusted such that the crosswire coincides with any one of the dark ring or central dark ring. The micrometer screw reading is noted. Main scale reading is in centimeters. Note down the reading of the coarse adjustment knob vernier 1. Multiply this reading with least count, which is equal to 0.001 centimeter. Note the reading of the fine adjustment knob vernier 2. Multiply this reading with least count equal to 0.0001 centimeters. The mirror M1 is moved very slowly using the fine adjustment knob, and simultaneously the number of dark fringes crossing the crosswire is counted. The mirror M1 is moved using the fine adjustment screw, and the readings are noted for every successive 25 dark rings that cross the crosswire. That is for n plus 25, n plus 50, etc. So the readings observed for the case of n are likewise MSR is equal to 8.6, VSC 1 is 68 and VSC 2 is 22. For n plus 25, MSR is again 8.6, VSC1 is 69 and VSC2 is 22. Now, when we move to the n plus 50th fringe, the MSR reading is 8.6. The VSC1 reading is 83 and the VSC2 reading is 23. And finally for n plus 75, we have the MSR reading to be 8.6, VSC1 to be 78 and VSC2 to be 85.
So this is the table to find the mean distance L moved by the mirror. So we are now going to note down the MSR reading, VSC1 reading and VSC2 readings. So when we place the cross wire on the first dark concentric circle or the central dark circle, the MSR value is observed to be 8.6, the VSC1 value is observed to be 68 and the VSC2 reading is observed to be 22. Now when we move from the nth fringe to the n plus 25th fringe, that is from the central fringe, if we count 25 fringes and come and place the crosswire on the n plus 25th fringe, the MSR value is seen to be 8.6, VSC1 is observed to be 69 and VSC2 is observed to be 22. Likewise, for the n plus 50th fringe, the MSR is observed to be 8.6, VSC1 is observed to be 83 and VSC2 is observed to be 23. So for the n plus 75th fringe, the MSR is observed to be 8.6, VSC1 is observed to be 78 and VSC2 is observed to be 85. Now we need to calculate VSR1 and VSR2. So this VSR1 is got by multiplying your VSC1 with 0.001 centimeters. So if we see, the VSR1 value for the nth fringe is 0.068. Similarly, your VSR2 is got by multiplying your VSC2 reading with 0.0001 centimeters. So the VSC2 reading is observed to be 0.0022. Now total reading is got by adding MSR with VSR1 and VSR2 and now we have the total reading got for all the fringes. Now we are about to find out the mean difference between the fringes. So we are going to determine n plus 50 minus n and n plus 75 minus n plus 25. So the mean distance is got to be 0.0152 into 10 power minus 2 centimeters. After finding out L, if we use this formula, we will be able to determine the wavelength of the source. So the wavelength of the monochromatic source of light in this case is found to be 6.08 into 10 to the power of minus 7 meters.